to the cloud. Great. Good morning. Today is November 9th. And I don't know about you, but there are certainly some small upsides to global warming. Today is a beautiful day. I am looking at people wearing shorts right now. I walked out of the house and was like, I don't need a coat. I don't know. Back when I was a college student, November 9th, you'd definitely be wearing a coat, maybe a little bit more. Running around in shorts just didn't seem to be it. Anyways, for those of you not in Boston, what was I just saying? It's a beautiful weather here at Boston University. And lots of people seem to have shown up for class. We got 6 people. Please pat yourselves on the back. All right, woo! What are we gonna do today? We're going to do something new. Basically, we're gonna do quadratic regressions. Woo! Drum roll, please. Okay, so is the Wi-Fi really being bad today or for anybody else? I don't know. I don't know. For me, the Wi-Fi seems okay. Anybody having problems with Wi-Fi here at BU? Actually, Joel, I don't know where you are, so I can't tell you. Wi-Fi problems for anybody in class? Nobody in class seems to be reporting Wi-Fi problems. Okay. All right, so what I'm going to do right now is I'm going to switch to our class website and show you what we're going to be doing. So share screen, go to our class website, and under resources, come on, you can do it. No. Under resources, we're going to look at lecture 17, forecasting cases. Lecture 17 is the one we need. And then under data files, I'm sorry, I forgot to move it up to the top last night. One of those ones that as I was walking into class, I was like, oops, forgot to do that. Where did it go? Big Bang is later. So what we want is income and happiness survey. It's right under children and wealth. It's about halfway down. Income and happiness survey. So those are the 2 files we need right away. Let me stop sharing. And share the PowerPoint forecasting cases. Please let me know if you cannot see the PowerPoint that says nonlinear terms. So, can money buy happiness? All right. In general, Questrom students should be thinking about this question a lot. Why? Because if we were to look at all the different undergraduate majors, which major at Boston University do you think provides the most money? Let me throw out a few examples. Philosophy, psychology, art history, business. Yes. So yes, there might be some other majors such as computer science that are definitely up there, if not beating Questrom students. But outside of things like computer science or some of the real STEM courses, you know, high energy particle physics and things like that, you are going to be in one of the highest paying groups. Does that mean your income is going to be the highest of anybody who graduates from BU? No, but on average, most of you will do quite well in life. And the question is, does financial success bring personal success? Are you going to be happy or not? So there's a whole bunch of different ways, theoretically, that we could see the relationship between income on the y-axis, money on the vertical, and along the horizontal, how happy you are. It could be a flat line. What does a flat line mean? Anybody online want to turn off your mic turn on your mic for a second and shout out what a flat line means between income?
Does it mean no correlation?
No relationship. Thank you very much. What if we saw a linear upward sloping line? Somebody else online?
Positive correlation.
Positive, but what does that mean in general? I mean, in simple words, so that my dog gets it. And by the way, I don't have a dog. I don't have a cat.
As money goes up, happiness goes up.
Excellent. So positive correlation, positive relationship, linear upward slope means more money, more happiness. How about exponential?
As your money increases, your happiness increases twice as much. Or
Exactly. Thank you very much, Gunsha. Definitely. And I think the voice before that was Kevin. Was that true? All right. I'm actually getting to recognize your voices. This is good because I can't recognize you by face now. All right. So exponential means as money goes up, so rich people are really like 10 times happier than poor people. Okay. And the left side of a quadratic, let's look at the next slide. So there's two parts to the left side of this. There's the upper one in blue and the lower one in red. Let's take both, the left side of the quadratic. So everything, one would be sort of this downward swoop and the other would be the upward swoop. Upward swoop is pretty easy. Okay, what does it mean? Upward swoop is pretty easy. So diminishing returns, I'm sorry, I forgot your name. I want to call you Michael. Sam. Okay, Sam. So Sam said diminishing returns. The idea is as you get more money, you get happier, but it becomes diminishing. So, you know, once I hit my first, say, million, I'm happy. My second million doesn't give me very much more happiness. My third million doesn't really change me at all. And between my fifth and 10th million or fifth and up to a billion, I'm the exact same happiness level as I was before. That's the red one. Somebody online want to do the blue one? Left side of the blue one. Left side, I mean, from the far left side all the way to the midpoint is what we mean by left side.
As you make more money, you lose happiness at a diminishing level.
Yeah. When you become really rich, you're basically miserable. It's like all these people are just trying to suck money out of you, you know? It's like, ah, man, I can't trust anybody. All right. So as you get richer, money makes you less happy. Interesting. I didn't recognize that person's voice. Who was that?
That was Alana.
Oh, okay, Alana. Hopefully I'll do better next time in recognizing it. So what we're going to do today is we're going to start today and Wednesday. We're going to start doing quadratic equations. We're going to start adding this so we can have these U-shaped functions. And what we're going to do on Wednesday, the penultimate, is we're actually going to look at hospital admissions in Massachusetts from COVID. And if we look at hospital admissions from COVID in the past spring, what we see is a graph that looks almost identical to the bottom, to the, is that a red line, the bottom one? Almost identical to the red line. That we had this pandemic, they shut down the state, hospital admissions started soaring, hit a peak, and then they leveled off. And this is going to be useful, or hopefully it'll be useful because they're expecting to have another wave very similar to it. And why do we want to be able to model these kind of things? As I'm going to say on Wednesday, if you actually have a very good model, you know where you're going to peak. You know how many people are going to show up in hospital for COVID, and we know whether we need to handle it or not. There's about 13,000 hospital beds in Massachusetts, and if the peak, according to our regression model, is greater than 13,000, then right now we need to start building field hospitals. We need to start building sort of temporary places. And if we're going to be less than 13,000 for COVID, then we don't have to worry. The hospital system will hold. So being able to model and make predictions, especially with quadratic things, are very useful even today in a practical sense. So let's go back and look at another example. Another example of quadratic here is GDP per capita, which basically means income for the average person in a country. And that's the horizontal axis. On the vertical axis is life satisfaction. And we see all these different kind of bubbles where the bubble is, the size of the bubble is equal to the population. So let's look over here at Norway, USA, and the Emirates. Norway has a small population. Emirates has an even smaller, so their bubble's smaller. In the United States, it has a big bubble, which means our population is a lot bigger than Norway or the Emirates. It's not to say that we're in a bigger bubble than any place else. And what do you see? You see an upward sloping relationship that I'm going to say matches a quadratic. So when we do a regression with a quadratic, a squared term in it, and that's what quadratic means, having a squared term, we can actually map all kinds of different things in life, such as this particular relationship. So if we look at country data, It's sort of the left side of the quadratic. What's the idea of the left side of the quadratic? As income goes up, happiness goes up, but as Sam pointed out, happiness is sort of bounded. So going from poor to middle class makes you very happy. Going from middle class to rich makes you a little happy. And going from rich to, oh my God, I have so much money, I don't know what to do with it. I should just donate it to Boston University, okay? Doesn't make you very much happier at all. It was a joke. I'm not telling you you have to donate it to Boston University, okay? Joke? No? Never mind. So what we're going to do is we're going to open up income happiness survey and graph the actual relationship between income and happiness. And I'm going to be quiet in a moment, but your goal is to put average income on the y-axis and happiness on the x-axis. And I encourage you to think about using a pivot table to quickly create this, okay? So can you graph income and happiness survey? Income's on the y, happiness is on the x. Does that make sense? So can you create that kind of graph? And I'll see you in about 3-4 minutes. Okay, and a couple of people in class here have already looked up, which suggests that they've finished. If you haven't finished, feel free to keep going or listen to me. So what the instructions say is put average income on the Y, happiness on the X, use a pivot table. So let me stop sharing for a moment and share my Excel screen. So what we have here is we have happiness and family income. And if you look at the description data says family incomes in thousands. What does that mean? So line 4 here, this family had $42,000 worth of income and their happiness was a level 6 and the maximum happiness is 7. So 7 is the most happy as a family. 1 is the least happy as a family. Looking at this line right here, this family had relatively little money. Multiplying this by 1,000 means it appears that they had $3,830 and their happiness was around the 4 or 5. So well below the poverty line. So what we'd like to do is like to create a pivot table. So we'll pick insert, table, pivot table. Make sure the blinking box is where we want it. It appears to be. We'll pick OK. And now we want happiness on the X side. So I'm going to drag happiness to the rows. I'm going to drag family income to the columns. And please stop me if you cannot see Excel right now. And I don't want sum of family income. Instead, I want the average family income. So I can highlight all this, make it money. And we can get rid of the pennies. And now if we graph all this, just put our cursor anywhere, pick insert, 2Ds, what do we see? A couple of things. One, we see a big spike here and we see a U shape instead of kind of an upward shape. So the question is, what's going on here with this number 1, 69,000? Because I have a really nice story here of basically a quadratic function, except for number 1. So let's take happiness and drag happiness to the values and count it. Drag happiness to the values and count it. Pick value field settings. Count. Pick OK. Let's get rid of the graph for a moment. And it's not dollars, it's just a count. So what do we see? We see almost 1,200 people answered our survey, but just 3, about 2%, are in this very bottom category. When we have large categories, like case 7, the family is very happy. We have 130 different families in there. For case 6, we have 500 families. Anytime there's somebody with a slightly higher or lower value, it sort of get washed out in the averages. But when you only have 3, one family having, relatively high income can really make the numbers look off. So the question is, when do you get rid of outliers? And when do you get rid of really tiny cells? What do I mean by really tiny cells? Really tiny cells are people who, there's like just 1 or 2 cases. Should we really be looking at that number 1 case? There's a couple of different ways of getting rid of it. One way is combining the 1s and 2s. So instead of having 3 in one case and 11 in another case, we just combine it and say less than 3, all the people with happiness less than 3, and we get 14 couples in that case. All right, a couple of simple ways of doing this. You could just go through the data, and anytime you see a case 1, happiness of 1, just make it a happiness of 2, and just in your description, call that 2 1s and 2s. So quick vote, please put up your blue hand if you're online, or if you're sitting here in class, please raise a real hand. How many of you think we should keep case 1? Or how many of you think we should get rid of it? So keeping it, let's keep case 1. 2 people said keep case 1, and online, I don't see any blue hands went up. So there's 35 plus 6 is 41 of you. We only had 2 votes. So we had about 3% for the 3% case. Just to keep things moving, I'm just going to graph this. So I'm going to copy it. In the real world, I would combine cases 1 and 2 all together. So what I'm going to do is I'm going to make this 14 instead of 11, and it's happiness of 2, 3, and I can use autofill. And instead of 2, I can say less than 3. Let's graph this. Insert 2D columns. And what we seem to do is something that looks like this. Interesting. Is that exponential or not? Could be, because the quadratic goes up and then comes back down again. So maybe it does fit a quadratic nicely. Let's jump back to the PowerPoint and look at some real world data. Here's real world US data, and what it has is it has income all on the horizontal axis and the fraction of the population who is experiencing something. And let's talk about not blue. That's the easiest one to understand. Not blue means you're not depressed in any way. Depression, however, actually has a clinical meaning. Depression, there's a whole bunch of things that you have to meet to be considered depressed, but not blue means sort of not, there's a difference between being happy and not blue, okay? If you're not blue, that doesn't necessarily mean you're happy, but in general, we sort of use it synonymously. Not blue means being happy. And what we see is as income goes up, happiness, not being blue, goes up, up, up until it sort of levels off. So about $80,000, it's not going to change your happiness feeling. Stress-free is easier. Do you have stress in your life? Do you feel stressed all the time? Let me say that I feel stressed up until the moment Zoom works. Then once Zoom works, my stress level really drops, okay? So this has been a very stressful semester for myself. And I think there's actually a third dimension here, you know, in the middle of a COVID-19 pandemic or not, as well as income. But what this graph shows is during non-COVID times, as income goes up, people's stress goes down, and then around $50,000, stress sort of basically flattens out. And you have sort of a certain level of stress, and more income does not lower your stress level. Positive effect says, do you frequently smile? Do you frequently laugh? Do you enjoy yourself? And for this, it's another 50,000, maybe 60,000, somewhere between 50 and 60,000, where you keep laughing and smiling up until your income hits sort of a level around 60, 70,000, and then it sort of also flattens off. So combining all three, you sort of get this ladder effect, and the ladder effect basically shows that as income goes up, stress goes down, feeling not blue goes down, and positive effect, which means laughter and enjoyment, goes up. Up till now, we've been using linear estimates. Linear estimates, things that are aligned. And what we introduced in problem set 4 was we did a squared term. It's one of the very last questions, sort of as a lead into today's lecture. And the question is, how do you tell if a relationship isn't linear? How do you know when to throw in a squared term or one of the other techniques we'll talk about in a couple more lectures? The easiest way, if there's only, go ahead, somebody just raised their hand.
Oh, I was going to make a guess to what I thought would make it something exponential per se. So when I was doing the problem set, I noticed that the t-stat was actually statistically significant for the exponential graph. I think it was like 2.5. So could it be that being statistically significant for exponential means that it is an exponential fit as opposed to a linear one?
I almost memorized this slideshow, but I believe exactly what you said is on slide 16, but it might be plus or minus 2, okay? So never give a particular number, always give a range. Ayush, that exact statement is going to be showing up somewhere between slide 14 and 18. Never give a single number. So great idea, but it's coming up either the end of today or beginning of Wednesday. All right, so how do you know, besides looking at the t-stat, which Ayush is already suggesting, another way is just to make a simple graph. By making a simple graph, relatively easy to see if you have curvature or not. So what we're going to do is we're going to open up another file right now, and it's called Can they see the PowerPoint? Great. We're going to open up salaries of business majors. And why did we create this data? Oh, we didn't create this data. Why do we take this data? Because all of you are business majors. Well, excuse me. Out of the 369 of you taking QM222, I think all but 6 or 7 of you are business majors. Okay, so the vast majority of you are business majors. And I'm sorry, ladies, this is just from gentlemen. It's all from males. It's not about females. We could do it for females too. All right. Linear relationship. Salary equals some constant plus years of experience. So I'm going to have you open up this file and run years of experience. And the problem is, does it make sense? Do these coefficients make sense? So 3 steps for you to do while I'm being quiet. Step 1, go to the class website, open up salaries of business majors. Step 2, look at years of experience and create the regression. Salary is the Y variable, years of experience is the X, and then interpret the coefficients. Do the coefficients make sense? Strong hint, not really. Okay? Okay. Once again, if you're doing well, keep going. If you're not doing well, you can listen to me. So our goal is to open up the salaries of business majors. I've already done that. And then run a linear regression where salary is the Y variable and years of experience is the X. And the question is, what's the extra year of experience? What's the value of an extra year of experience when you have nothing, when you're just fresh into the job market, versus when you have 30 years of experience? So let me stop sharing and switch over to Excel. Share screen. And could somebody shout out a number between 2 and 31, but please only shout out if you're very shy and feel that you have no class contribution. So we know who the people are who need some help.
19.
Who was that?
It was Maran.
Marab, great. 19, you said?
Yes, Professor.
Great. So Marab picked line 19. Let's read line 19 out. Line 19. Well, my cursor seems to have stopped picking things. Line 19 says this person has 23 years of experience and $75,000 worth of salary or income. Okay, so what we want to do is we want to do in data. Well, we'd like to do data. For whatever reason, Excel is not working, so let's see what else we can do. Data, okay, data analysis, regression, click OK. The Y range is what? Anybody else who needs a little help with the class contribution? Ashley.
Salary.
Okay, so salary is A1 through A3,449. And the X range is experience, which is B1 through B3,449. We have labels in the first row. We can pick OK. Clean things up. Make things easy to read and understand. We can get rid of the repeated upper and lower 95%. We don't need multiple R. We don't need the ANOVA table. And we can format the coefficient, standard error, and upper and lower 95% as money because salary is the right-hand side variable. Format the upper and lower 95% as salary, as money. And the R squared and adjusted R squared get formatted as percentages. And the standard error of the regression gets formatted as money also. What does this say? Can someone tell me what the R square and adjusted R square value tell us?
Is it how well like our data fits our model?
Okay, so if this was a final exam question worth 4 points, that's an answer that worth 2. Completely correct, but only half credit. Why is it only half credit? Because it wasn't precise. All right, so let's make it a little bit more precise without going crazy. Anybody else online?
Salary describes 5%.
I'd flip it around. Experience
Describes
about 5% of the changes in salary. So if I'm trying to figure out what salary is, experience by itself explains 5%, and other variables explain 95 that we don't have in our model just yet. And Ritvik, please give these 3 charming people full class contribution because they're all like, pick me because I know what the answer is. Okay, so the R squared tells us experience alone explains 5% of salary, and we're missing 95%. The T-stat, the standard errors, the t-stat, the p-values, the standard errors, all show that these numbers are highly significant, that there's no chance that there's zero. Now, if somebody was to interpret the intercept, what does the intercept say? Somebody online who hasn't spoken today? Max, go for it. Iris, you're next for experience.
Is it with 0 experience, the average salary is $57,000?
Exactly. No experience. Typical person makes, a business major makes about $57,000 on average. So getting out of questrom, you should be getting about $57,000 if this data are accurate. Let me just say with COVID, we have no idea what salaries are starting to be. It's, you know, the whole world has changed. Could be higher, could be lower, could be the same. Iris, do you want to do experience?
Sure. For every year of experience, they gain about like $1,800.
Yeah, every year of extra experience, you gain about $1,800. So work for a company 2 years, you get an $1,800 raise. 3 years, another $1,800 raise. Next fourth year, you get another $1,800 raise. And the slideshow said, does this make sense? Raise your blue hand if you think it makes sense. So we have 4 people, 6, 8 online. How about in class? 10. We have 2 people, 3, 4 in class, 5 in class, 5 out of 6 in class have raised their hand. So we've got 17 out of about 41. So we're a touch less than half. Thank you very much for raising your hand. Let me say that in the real world, this doesn't make sense. You will get raises the first 5 to 10 years of your life in the working world. And after that, raises will only show up when you get promoted to a different job, different experience level, or work for a different company. Other than that, your salary stays fixed. I worked at Ohio State for 23 years. The last 13 years I was there, basically they changed my salary by inflation. I've worked at BU a while. I can't tell you the last time I got a salary raise. I mean, they bump you up for inflation, but it's not like, woohoo, let's give you an extra $2,000 because we love you. All right. After you've been there for a while, raises stop coming. In the beginning, raises come relatively frequently and in a relatively large amounts. So what does that mean? If we graph things, share screen. If we graph things, hopefully now you're looking at the PowerPoint, what you see is you see something that looks like this. If we have experience versus mean income, first 20 years or so of your life, you'll get raises, and after 20 years, basically you don't get raises anymore. Income basically flattens out. And that is what I found in my own personal life. That when I was younger, I got raises all the time, and as I get older and work for organizations longer, this doesn't happen anymore. Okay. So how do we capture, was that a chat that went by that I needed to deal with? Okay. How do we capture nonlinear relationships? The easiest way is to add a squared term. So we have salary, and then instead of experience, we have experience squared. And then we're going to run the regression on experience and experience squared. And this is the Ayush slide here. I'm sorry, Ayush, I said slide 14 to slide 18. It turned out to be slide 13. I was off by 1. I hang my head in shame. I'm sorry. You keep both the linear and the nonlinear term if they're both statistically significant. If the squared term is not statistically significant, throw it away and stick with the linear model. So let's jump back to the Excel file. Go back to the data. And what we want to do is we want to create an experience squared term. So we type experience, and I type, I don't know, S squared, there. Experience squared, XPR squared. And to do an experience squared term, it's relatively straightforward. It's equal B2. And there's 2 different ways of doing it. We could do a caret, which is on my keyboard, Shift 6, a caret, which is on my keyboard, Shift 6, 2, which means square B2. And that gives me 484, or we could say equal B2 times B2. B2 times B2. Both are the exact same thing and will give us the exact same answer. 484. And then what we need to do is double click and do an autofill. I got 484 for the first number, 9 for the second number. Let's jump to the bottom. I got 9 and 49 for the bottom two results. Did you get something similar? So I'll be quiet for just 1 minute. Can you run a regression where salary is the Y and experience squared is the X? I'll give you a 60-second head start. All right, 60 seconds are up. So we pick data analysis regression, okay. The Y range is the same, and the X range is B1 colon C 3,449. C 3,449. Click OK. Let's clean things up real quick. Upper and lower 95% repeated. Repeated is boring, boring, delete, delete. Multiple R we don't need. Now we can kill the ANOVA right now. R square. What happened? By adding an experience squared term, we boosted the R square up to 6%. Not bad. We improved the fit of the model without actually finding any more data. We improved the fit of the model without finding any more data. That's pretty good. Usually you have to find more data to improve the fit of the model, but we didn't. We just got a better fitting. Let's look at the coefficients. I'm going to highlight the T-stats in yellow. Somebody help me out online who has not spoken already. Intercept, experience, and experience squared. Are they statistically significant? Yes or no? Somebody help me. Holly, go ahead.
Yes.
And why?
That they're outside of the absolute value of 2.
Okay, both bigger than the absolute value of 2. Excellent job, Allie. Please pat yourself on the back. Okay, so I don't have time to switch back to the PowerPoint, but the PowerPoint slide, the very next one says, what is the effect of an additional year of experience on salary with someone with no experience? So using this model, what is the boost in salary if you go from no experience to 1 year of experience? And then the PowerPoint also says on slide 14, what's the effect of somebody with 25 years of experience? So going from 25 to 26. So the first one is 0 to 1, the second one's 25 to 26. Okay. Easiest way to do this, insert a blank column, we'll type values. Intercept is always 1, and the experience is, how do we get 10, 26? The intercept is 1, and experience the first time is 0, and experience squared is equal to A11 times A11. Predicted salary. And what's the predicted salary? The predicted salary is equal to the sum product of the value column A10 colon A12 comma C10 colon C12. And if you have no experience, how much money you expected to earn at this company? About $29,000. No experience, you earn $29,000. Please remember that. Let's change experience from 0 to 1. And you get bumped up to $35,000. So how much was the boost going from 0 to 1 year? Go ahead, Allie.
5,842 is what I
Thank
got.
you. Excellent job for being precise. How about 6,000? Yeah? No, maybe? Okay. I think Allie's nodding yes. Great. Now, the other question, since I have only 90 seconds left, the other question on slide 14 was, what is your salary at 25 years of experience, and how much of a raise do you get from going from 25 years of experience to 26 years of experience? Pretty straightforward. Type 25 into cell A11. And that person makes $108,000, we'll call it $109,000. $109,000. And now let's change 25 to 26. And what's the difference? Well, I guess we can't round because this is 108,943 and this is 108,634. The difference is, how much was the boost by going from year 25 to 26? Less than $300. How much was the boost going from year 25 to 26? About $300. I'll tell you, since I have only 15 seconds left, a quick personal story. One of my last years at Ohio State, the boss said, "Congratulations, Jay, we loved you. You had a great job. You did great work for us this year. Here's your raise." And the raise was $225 after taxes. It was less than $200. And I said to my wife, "Woohoo, let's go for a small meal out in celebration and blow the entire raise." But the boss sent me this glowing letter. You did a great job, but sorry, you've been here a long time. We don't have any extra money and you're not getting anything. So I was like, okay, thanks, boss. At least I have a job here. Thank you very much for listening. I look forward to seeing all of you on Wednesday. We're going to continue on experience and experience squared. We're going to do COVID, and hopefully we'll do the Big Bang Theory. Let me ask a real quick question. Does anyone still watch the Big Bang Theory? No.
I watched the reruns.
Yeah, that's, the reruns, right. Have any of you heard of the Big Bang Theory? All right, people have heard of it. All right, so I don't have to go find another TV show. All right, great. Have a great day. See you soon.
Professor, I had a quick question.
Sure. That
Could
sounds
you?
like Serenity. Is that true?
It is. Yes, it